All right, y'all. First of all, I have to cop to the fact that I know that I'm late with the grades. Next time, I'm definitely going to prioritize that higher. But I thought I would do it during break, and instead I spent time with my wife. So good for me, less good for you. Definitely top priority once I'm done with this class. So copying to that, and here's a promise to have a faster turnaround for the next set of exams. That's especially relevant because we have another take-home exam coming up. So it's going to cover the generalized linear model and data management. For the data management content, a lot of this is like pretty practical, right? So the kind of thing that you can expect me to do is give you a messy data set and say clean it in these ways. And I'll give you instruction, especially because there's a little bit of ambiguity about what counts as a tidy data set, what counts as a group, and what doesn't. So I'll be a little bit more specific about how I want the data set tidied, and then I would ask you to do some transformations or something like that, do some simple work with data.
That's this Brian.
Yes. Right. In terms of where we're going for the next couple of days, the content we're going to be covering goes a bit beyond the Levenstein and Lyle paper and the Hadley Whitman's tidy data paper. I couldn't find any particular readings that really fit what I'm covering next. And in any case, I want to limit the amount of reading that I assign. Some of what I'm going to be covering today and on Wednesday is more for your information, like these are ways to help your workflow be more efficient. So I'm not expecting you to know absolutely everything that we cover, but I will be hitting on some big picture ideas that I think are important and useful. Questions on that? All right. So it's been a little bit since our last class, so you might not be in quite the same headspace as you were before spring break. You shouldn't be. I hope you did take some time to relax. So just a brief overview of what we were covering before spring break. First big picture idea is that this thing called data management, that's like all the processes that go into how you curate your observations, how you make them useful for analysis, is guided by 5 big picture principles. The first of these is ethics. So making sure that, especially if you're dealing with human subjects data, making sure to keep those data confidential. The second is security. So I talked a bit about backing up your data, making sure that you're protected against data loss using systems like Dropbox or the Open Science Framework to make sure to duplicate your data. Accuracy, so protecting yourself against coding errors. Usability, so making sure that your data can actually be used for useful purposes after they're reported. And transparency, so making sure that we're being clear about the processes that went into producing a given data set. We've already talked a bit about how to make data useful. So I talked about data set structure and how certain structures tend to be more useful than others. The sorts of things that I'm going to talk about today also bear on some of these last 3 principles: accuracy, usability, and transparency. Particularly usability, and where we're going to go for the last class is bringing some of these concepts together that we've talked about in the last 3 classes to try to maximize the accuracy of your data set, to make sure to do good error checking and catch observations that might be miscoded or something like that. So we also talked a bit about the different types of data that you have in a scientific project. So I made the distinction between source data, which is as close as possible to the thing that you want to observe. So that might be pictures, videos, it could be actual like paper copies of surveys, as close as you can get. Raw data is very likely transformed version of that source data. So it might be numbers that are used to represent the videos, or transcriptions of written surveys. Process data is data that you prepped for analysis. So you've actually done a few more transformations or restructured the data set in some way. And then metadata is data about your data. So it tells you something about the processes that went into each of these different steps. And one of the big picture ideas that I talked about in this section is that you always want to keep copies of your source data. And you also want some information about the processes that you use to get from the source data to the raw data, and the raw data to the process data. So that should be scripts or documentation, whatever it might be, you want to capture that information as well. And then finally, sometimes you have a distinction between raw data and process data, sometimes you don't. It really sort of depends on the nature of your project. And then the last thing that we talked about on Wednesday before we broke the break is this idea that certain data can be structured in more useful ways. And in particular, there's this type of structure that tends to be quite nice to work with. That's called a tidy structure. The idea behind a tidy structure is that your data represents, they're all values that can be categorized into variables, which is like a common type of measurement, and cases. So a case is a grouping of variables that applies to a specific observational unit, like a person, a school, it could be a business, any sort of unit of interest that is of interest to you scientifically. So data are tidy when each variable is a column, each case is a row, and if you have separate observational units, you want those to be in separate tables. That said, something that I touched on Wednesday is that you don't always want the maximally tidy version of your data for analysis. There's certain analysis tools that expect somewhat untidy data. So the important idea is knowing how to restructure your data to go from tidy to untidy versions, so that whatever it is that you need to do, you can do it based on whatever tool it is that you're using. And generally, when you're restructuring your data, you're like adding some rows and compressing information to change your columns, or you might be taking labels in the columns and using those to form new variables in the rows. There's a couple functions in particular called gather and spread that take a data set that's somewhat short and make it longer, or a data set that's wide that has a bunch of extra variables and makes it longer. So today we're going to talk about a bit more about data set structure, like what's going into raw and processed data. And specifically, we'll talk about what your column headers ought to be. It seems like kind of mundane thing, but it turns out just as with data set structure, there are better and worse ways to label your column headers. And it turns out that that can be actually kind of a big deal when it comes to analysis. Hadley Wickham, the guy who wrote that tidy data paper, says that about 60 to 70% of his time as a data scientist is spent cleaning data, doing things like making sure that the variable names are meaningful, that they're good variable names, and then getting data into particular formats for specific types of analysis. He's a professional data scientist. He has way more experience than I do doing this stuff. So I trust his professional judgment. If you talk to data scientists, a lot of them will say the same thing. This is like the bulk of their time, cleaning data, and getting into good formats, thinking about good variable names, thinking about how to structure it in the most useful way. So to give you some intuition about like what might count as a good variable name or a bad variable name, I've got a couple sample data sets. I just want you to tell me, like, what do you think is problematic about the names of the variables in each of these data sets? So here's one way I could choose names for this data set. Is there an issue with this? Yeah. And why would it be a problem if they're all the same name?
We don't know which variable it's like.
Yeah, I mean, often we want to reference a specific variable. So you want to pull out that variable and then calculate a mean or use it in a GLM. And if two variables are named the same thing, then you can't, when you're trying to do this in your computer in R or whatever program you're using, there's no way to tell, for the program to tell which column is which. It's also, it might be a problem if you're like thinking about the data on your own or staring at a couple rows of spreadsheet, you're trying to figure out what to do with your data next. I mean, if your columns are all named the same thing, that kind of repeats your thinking too. Okay, so I've made these columns, or I've changed these columns so that they have different names. So do you think this is a good system for naming? Yeah.
I don't think so, because it doesn't which variable you're looking at. It's just like, if I'm looking at variable 2, what am I really looking at? I have to look at it in the coding book. It just makes it more difficult.
Yeah, did you have something to say?
It's just too big.
It's pretty big. So all of the scientific context is completely gone from this data set. I'm just looking at words and numbers that are pretty divorced from the scientific problem that you want to solve. I don't know if this data set is relevant to emotion or if it's relevant to some sort of health intervention. If I'm looking at medical data, all that context is completely gone. So I'm able to distinguish each column from each other. And if I'm working with a computer program, so if I'm working with R, for example, I could fit a linear model that predicts bar 1 through bar 2. The computer program doesn't care necessarily what these are named as long as they're unique. But for my purposes as an analyst, or your purposes as an analyst, these are pretty bad names because you want to know something about the scientific problem. You aren't necessarily specifically concerned about these numbers. It's the scientific problem that's driving your interest, not these particular numbers. So that's an important point actually, because it shows that what's good for the computer is not necessarily good for you as the analyst. So the names that you choose ought to be useful to you, not just useful to the computer. They do have to be useful to the computer, but they also have to be useful. This is a slight variation on that that naming convention I just showed you. So I've added commas that separate bar from one. Anybody think about, or does anybody have an idea why that might be?
Well, and commas and are in some other processing systems that might actually inadvertently separate bar from that number, and so it might not read it as one variable.
That's a great observation. So one very common way of storing data is called a comma separated value. It's literally a text document with commas to indicate which column is which. So the structure of this data set is literally something like, I'll go back one. It's something like R1, R2, R3, and then the new line, 1, 1. If you open a CSV file using a text editor, a basic text editor, so WordPad or Iron with the MacBook, you literally just see a bunch of values with commas that separate the rows. So if this happens to be how my data are stored, that can be an issue, especially if you're using CSV as your storage method. Other common separators are tabs. So a tab separated value.tsv extension, that's another very common way of storing data. It also sometimes has the extension .dat. The really basic ways of storing data often use special characters as a way of indicating which column is which. You don't want to use those characters as part of your variable names, because no limitations. So this is another of those things that helps the machine deal with your data set. You as the analyst don't necessarily care whether you use commas in the variable names. The computer will. Okay, so same data, but I've changed the variable names. What do you all think of these variable names?
Mostly okay, except for I would not want a condition to be capitalized, and if RT is reaction time, reaction time, none of the other ones are abbreviated, but that's just.
Yeah. Any other thoughts? These are pretty good, I agree. So one thing that's changed is that instead of ones and twos, this is a condition variable. I've changed those ones and twos to control versus experimental. So one reason that that's a nice thing to do is if you're analyzing your data, you don't really care whether, under the hood, R is representing your data as ones or twos. You care about the text labels, control versus experimental. So by replacing the numbers with the text, you're getting closer to bringing in some of that scientific context that's important for interpretation. You might imagine if you, I don't know if this has happened to you before, but if you're analyzing data and you see a bunch of ones and twos or minus a half and positive a half, you might think like, okay, which conditions which in? That's something that often happens. This is a way of making sure that you have some of that context. So that's one nice thing about this way of naming the variables. Another nice thing is that we now have like some of the meaning, the context of this problem represented in the headers. So we know now that we're working with a condition variable. We know that we're working with emotions, probably Likert scale readings. RT probably means reaction time. At least I think you can take an educated guess. So there are a lot of things that are really nice about the way these variable names are structured. But one problem is that the formatting of the variable names is not consistent. So you might imagine if you're trying to analyze your data in R and you're typing along, if you try to fit a model with condition predicting happiness, you might run into that problem, well, should condition be capitalized or not? That's one very common way of having errors. And sometimes these errors, these bugs can be difficult to detect. Well, one way that you can prevent that kind of errors, that kind of bug, is by formatting your variable names consistently. So rather than having a mix of capital letters and non-capital letters, you choose one and stick with it. Or at the very least, you have a consistent rule about when to use capital letters. So there's nothing inherently wrong with capital letters. Just make sure that they have some sort of meaning. Okay, here's another variation of these variable names. If you don't know, not all of you are from psychology here, but the PANAS, the positive and negative affect scale, that's a very common scale for measuring positive and negative feelings. What do you all think of these variable names? Yeah.
I think they're better, but it's weird that it's like coffee PANAS and PANAS scale.
Mm-hmm.
So you use a different convention.
Yeah, this is another problem with the system that's used to name its variables. So again, this is another thing that might easily generate bugs or problems if you're going along with coding. This is another place where the computer doesn't care whether it's happy PANAS or PANAS happy, but you as the analyst might care. And it helps your thinking to have things be consistent. Here's one final one. What do you think about this? Yeah. Yeah, that's maybe something that could be improved. I'll talk about that a little bit later because there's some considerations with whether to add something extra to separate participant from ID. But in general, this looks very good. It's one thing that I hope you notice is that immediately by looking at variable names, it provides some information about the structure of the scientific study. So we don't know all the details of this study, but we can probably make an educated guess that we have multiple participants in different conditions who took some sort of Likert type measure and did some sort of reaction time test. So big contrast from the first data set that we started with. These different systems for naming variables are called ontologies. That's a fancy word. All that means is it's some sort of way of representing stuff with groups. Ontology in philosophy is, I never took philosophy, so I'm a little bit off my depth here, but as I understand it, it's the study of things and what they are. An ontology in information science is a way of assigning text labels to stuff out there in the world and defining their relationships to each other. So this is a formal branch of information science. If you talk to a library scientist, they can probably tell you a lot about ontologies. It also comes up in data set structures. There are lots of ontologies out there. So if you think about the Latin system of assigning names to species, that's an ontology. The different ways of thinking about wines, so red wine versus white wine, with all these different descriptors for whether something smells grapey or has sort of an earthy aroma, that's also an ontology. any way of assigning words to concepts and defining the relationships between concepts is an ontology. So if any of you deal with pre-response data, if you develop, say you develop what's called a coding scheme for getting specific information out of that pre-response data, whether the person is angry or satisfied or talks about the relationships, any way of extracting less rich information from the set of text, that's also an ontology. So ontology is just a way of assigning labels to other concepts and then thinking about the relationships between concepts. Good ontologies for naming variables in data sets have a couple different characteristics, and we've gone through all of these in one way or the other with those examples. So first, you want each variable name to be unique, so you don't want repeats. If you have repeats, then you can't tell which variable you're referring to when you refer to bar, for example. So a good ontology allows you to distinguish one variable from another. This is a bunch of concepts bundled together into one overarching idea. But you also want names that are descriptive, that you can just sort of read off of the top of your spreadsheet, or if you use the head function in R, that you can just sort of read off the top there. And they should be memorable. So if you're typing along and trying to remember whether your variable was called guilt or something else, that might be a sign that your variable name was an ID. It can be a real art to figuring out which variables are going to be meaningful to you. And if you're trying to make variable names that other people can use as well, that can be a real task. But this is one way that you can evaluate whether you have good variable names. If they are memorable, if people can just sort of read off what they are, they understand basically what the variable is, and they can recall it when they need it. That's a good variable name. Good variable names also are consistent in the sense that their formatting is consistent, but also consistent in the sense that if you use a noun to describe one emotion, for example, so guilt, you ought to use a noun to describe another emotion, so anger. So you shouldn't be in a situation where you have guilty plus anger, because that's going to be harder to remember. If you use one way of describing one variable in one place, you probably ought to use that same way of describing your variable in another place. For data sets, you also want an ontology that is machine friendly. So what that means is that you limit the amount of punctuation. Some punctuation is fine, but there are a couple types of punctuation where you can run into problems. One in particular is commas, another is tabs. Personally, I prefer not to use periods either. I know Austin uses them, and he has a workflow that works for him. One reason I don't like periods is periods are often used as extensions and say variable name or file names. They also come up as special characters in other places too. So personally, I have preference. A couple useful types of punctuation is the underscore. That's not, as far as I know, that's not used in any common storage format. Dashes are also good. So some punctuation is fine, but you should limit the amount. You shouldn't use like weird punctuation that might one computer might have but another doesn't. And especially try to avoid commas. Spaces are another one that you want to avoid for columns. The last big picture idea is that the way you name your variables ideally ought to tell you something about the way the underlying scientific project is structured. I've already pointed out a little bit about how just by looking at a snippet of that last data set, you can sort of tell something about what that project is about. That's the idea here. So if you're careful and with how you name your different variables, that can give you some idea of what the project is like, even if you don't have access to the full project description. So I want to focus on this idea a bit more because it's a tiny bit less obvious than the others. So first of all, let's think for a second, what are some elements of the structure of scientific projects that you might want to know about? So variables that go together, or what are things that could make variables go together? What sorts of aspects of the structure of scientific projects might you want to know about when you're looking at a data set?
Maybe if there's like a pre and post measure or like that.
Repeated measurements, great. So if you have measurements that are taken multiple times, that's something that you want to know about. What else? Yeah.
Actually, whether it's an experimental design or a field study.
Oh, that's an interesting one. Yeah, I don't have offhand. I can't tell. Right, I'm having trouble thinking of what you need to sort of solve the use of that. That's just like in the variable names, but there might be a way. But that's an interesting one. Yeah. What else? Think about anything that might link one variable to another, or one row to another. I'll go back a couple slides, see if that helps you think of one at least.
So they're from the same measure?
Yeah, so if you have multiple variables from that go together in some way, like this has been always looked at the same instructions for all these items, and then for each item it's a different stem. Are you feeling happy? Are you feeling anxious? Whatever. What else?
I guess it's good to know about the different types of measures, like reaction times probably, the seconds, and the happy deal with maybe the liker scales, so we have different kinds, so you have different analysis.
That's good, and there's often a term in specific projects for like a set of measurements that go together.
Mm-hmm.
What might be a good term for that?
Like a scale, maybe a composite
Scale. Sometimes you get these things called blocks, especially if you're using reaction time measures. So a block is just a group of responses that go together. So often, especially in psychology, we have blocks and trials that go inside blocks. You might have multiple things that you measure about a given trial too. So maybe both the speed of the response and whether the response is accurate. Yeah.
You also might want to know like how that variable is computed, like for reaction time, like whether or not it was a different score, or like whether it was mean centered or anything like that.
Yeah, great. So often we apply transformations to one particular variable or set of variables. So one transformation might be a difference. You might want to know both things that went into the different score and different score itself, you might want to know that those three things go together too. You might have mean scores that, so you take the average across a bunch of items or whatever. You probably want to know that these items go with this aggregate, this mean. Right. Anything else? Sometimes you have, so in this data set, it looks like different participants experience different conditions. Sometimes you have a project where each person experiences multiple conditions. One way to represent that would be to have multiple columns, one per condition that the person experienced. So you probably want to know that, hey, these are the same type of response, just given under different conditions. Another piece of information that you might want, let's say that you have multiple pupils in a given classroom, but you have separate classrooms. So that's another thing that might link multiple columns or rows together, whether there's, they're from the same classroom, or whether it's sort of similar to the fact that you might want to know that these are multiple measurements that are given at different points in time. Similar. Anything else? So we listed a lot of stuff. And it's hard to give a comprehensive sense of all the different things about a project that might link responses together. So this often requires some thought about what information you as the user, as the future user, might want to have about this project just by looking at the column names. And also what information other people might want if they're coming into the project fresh. So your advisor person, or a collaborator, or if you hopefully convinced many of you of the value of posting your data publicly, if you plan to do that, that might be, those future users might be other people who might want to have this information. Here's just a list of things that come up in psychology. I think we've covered most of these. One that might not occur to you, but as that I've dealt with some, and some of my recent work is sites. If you have multiple sites that are all doing multiple labs, for example, that are all doing the same project, that's something that you might want to know. Stimulus. So often in psychology or behavioral science, you have, say, the same picture that multiple people see. So it might be a picture of something that we discussed or two ago we discussed. Well, you probably want to know that this particular response that one person gave is the same picture as this other response. So that's another type of information that you might want to have. Task, sometimes you have like a group of blocks that all belong to one task, like this group task. Another group of blocks that belong to a different task. And you have each person doing multiple tasks in a given session. Point being, this varies a lot because science is really varied. And it can take some work to figure out, okay, what information do I want represented in my data set in a really accessible way? Another important point about all of this is that some of this information will be encoded in a tidy format. So you don't always need to represent each of these things in the variable names. Sometimes they're represented just by the way the data are structured. So for you to see this, I showed this animation before. Notice that this is the tidy format. In the tidy format, my variable names don't have to do as much work as in the untidy format. In the untidy format, if I have these two different variables, each of which has two conditions, my variable names need to give that information for all four columns. Whereas it ends up just kind of being encoded in the values once we go to a tidy format. In general, if you go from an untidy format to a tidy format, your variable names need to do more work in the untidy format than in the tidy format. To give you a sense of what this, to be a little bit more concrete about this, if I have depression measured at 2 times, in the untidy format, I need to have 2 separate columns. Depression time 1 and depression time 2. Whereas if I transform this into a tidy format, I can just have a variable called depression and a variable called time. And the work of distinguishing between time 1 and time 2 is done in the context of the time variable. It doesn't have to be encoded in the variable. Does that make sense? But one big picture idea is that, I've already mentioned how sometimes you need the untidy data set to do specific tasks. So you ought to have a way of representing both the tidy data and the untidy data. You want the way you name the variables to work with in both structures. So that's a lot of stuff that you want an ontology to do. It would be really nice if in the behavioral sciences, psychology, economics, business, whatever, we had standard ways of naming variables, so that we had a standard ontology that we all use. That would be super, but we don't. Actually, these are ideas that, are barely ever taught in data analysis classes in psychology or the behavioral sciences, or at least they are taught. I've yet to see the class. So this is something that's often left to the individual lab, investigator, whatever, to think about, get this thought about at all. If you do think about this stuff ahead of time and plan out how you want your data to work, to look like, it can save a lot of time, and it can make things more efficient. And I'll show you how that works in just a bit. But main idea right now, this is something that these are decisions that you have to do. I do encourage you though, if you choose a specific way of representing your naming variables right now, I encourage you to use that across your projects so that you don't have to reinvent the wheel at a time. So try to be standard with how you do these things, that if you go back to old projects, that can save a lot of time. But there's no field-wide standard that I know of for you to use. So what you do with your variable naming conventions, it's a little bit up to you. It's what makes your life easy, what makes life easy for your collaborators, your professors, your class, or whatever. One that's worked for me, or one rule of thumb that's worked for me, is an ontology that looks kind of like this. So early in the variable name, you have information that's relevant to the structure of the scientific project. So trial 1, log 1, whatever. Separating each piece of information, you have an underscore. In the middle, you might have information about the specific variable. So depression, anger, happiness, salary, whatever. And then at the end, you have information about any sort of mathematical transformation or operation that you've done. I have to admit, if I look across my projects, I've not been totally consistent with this ontology, partly because I haven't thought about it in a systematic way. I just sort of picked that this is stuff I picked up as I've progressed in my scientific career. But something like this, I think, works pretty well. So a couple things I'll point out about this type of ontology is that I've tried to standardize the format. I like all lowercase because I don't like having to press the shift or type. Just makes things a little bit faster for me. The ordering is meaningful, the order in which I place information, which also means that if I need to construct a new variable name, it's pretty easy to do so. So if I do a transformation into an old variable, I just stick an underscore log at the or underscore n. Anytime I do that transformation again, I'm going to come up with the same variable. This also tells me stuff about my project if I'm going into a data set that I haven't used in a long time. So this tells me the variables I'm working with, something about what I've done to come up with any constructed data that is new or that I've created through a transformation. And it also tells me something about the structure of my project, even if I've, for some reason, lost like the little method section of the however I stored that metadata. Just by opening up the data set, I get some of that information, which is quite nice. The last nice aspect of this way of naming variables is that there's a consistent separator and it's not a comma. So I use the underscore for my separator most of the time. One thing that I thought about doing, I haven't implemented in my own projects, but I think it makes sense, is if I have say a variable that is multiple words. So let's say the back depression inventory. You can use a different separator besides the underscore to separate those words. So what I mean by that is participant ID. I had a data set that had a participant ID at the top left. So instead of writing participants ID, that's a little bit hard to read, you can write participants dash ID, which is slightly more readable. That's not something that I've done before, but I've been thinking about making a change. Again, anytime you change the system, it takes time. So that's something you can do on your own. Whatever works for you, whatever is intuitive to you, as long as you're following some of these other best practices. Questions on that? So if we go back to the last data set where we landed, I think I already mentioned how just by looking at the variable names in this data set, you can intuit important aspects of the structure of the project. So again, the participants took the pianist, and I recorded happiness and guilt. each participant only experienced one condition. And there are probably other variables in this data set that went into this reaction time difference. There's probably even a lot of trials related to that task that all create that positive. And that's something that you get just by looking at this data set, which shows how much work a good ontology can do if you're thoughtful about what you use as your variables. Any questions? Okay. So I've described a little bit some of the benefits of like just sort of thinking about this stuff. You know, you open the data set and you get some immediate information about the structure of the project. But there are some technical benefits that really help with data cleaning, which is what we'll talk about in more detail on Wednesday. Those are hard to understand unless you know a little bit more about programming. So this next section is going to be a little bit programming specific. I'm not expecting to know everything from this section. I'm going to give you some tools that will hopefully make your life much more efficient.
Random question, what was the difference between data cleaning and data wrangling?
Data wrangling is, people often use that to mean like restructuring data or merging data from multiple sources. Data cleaning means making sure that the values that are stored in the data set are actually accurate. Does that make sense?
Yeah.
Other questions? So this data set is a snippet from that NIH data set that I've used a couple times throughout this class. So first of all, notice that I'm not consistent in this data set with how I use the underscore. So, you know, I'm still learning about this stuff and thinking about it too. One thing that I did do though is in these last few columns are all grouped together under a scale that's called concern. Specifically, what the participants did is, you know, this is a snippet from Qualtrics. They have the same instructions prompt at the beginning, and then they have multiple items, all of which use the same scale. So, okay, I've always preceded the specific item with a concern and an underscore to group those together. So that bit of information is represented in the data set. I can use that information to help select in a very fast way all of the items related to this concern scale. And this is where the machine benefits, the efficiency benefits kind of come through. A lot of what I'll be talking about is related to this package called Stringer. Stringer is an R package for manipulating bits of text. Turns out if you use a common ontology, that can really help if you know something about how to manipulate text in a programmatic way. Stringer has a lot of different functions, and I'm not expecting to know all of them. But I do want to make you aware of them because if you need to do something with text, you know, chances are Stringer can do the task for you. One that I do want you to know something about is str_detect. What str_detect does is it returns a true or a false if a given chunk of text is found in some sort of collection of variable names, for example. So what I can do is I can look for that stem concern underscore across all my variable names and pull out the names of the variables that have concern underscore, which allows me to select those in a very fast way without having to like look at a spreadsheet or consult my code book or whatever other process that you might do. So I'll show you how this works. The way you use stringer is that you give it the string or the set of text that you want to search. So the variable names, for example, and then you give it the pattern that you want to search for. So for example, I can use str_detect to look in each of the column names, the variable names of the data set that I'm working with, and search for concern underscore. And what it's going to do is for each column name, it's going to give me a true or false if that if concern underscore is found in the column name. I've only used concern underscore to indicate variables that belong to this concern scale. So this is only going to be true if the variable in question is one of these concern items. I can then use these brackets to say, okay, look in the column names and just give me the name of the column if it is true that concern underscore is found in the column name. So this is selecting the column names where this condition is satisfied. And that gives me all the items belonging to this concern scale. If you just want to copy and paste, the things that you would need to change are the name of the data set and the thing that you're looking for. But I'm hoping that you can sort of get the logic of how this bit of code works. Questions on that? I can then save the names of the concerned variables into their own object and do stuff with these variables. So for example, if I want to take Chromevox alpha and then take a mean, for example, I can reference those names of those variables when I use the alpha function or the row means function or anything else. So if I'm doing a bunch of stuff with a set of items, this is a very fast and efficient way of doing all those things. That takes a minimum of code. It minimizes the chance of typos because you don't have to type in those variable names yourself. And that's all enabled by thinking a little bit ahead of time about what units in your data set you're going to want to work with. And thinking, oh, I probably going to want to know whether each of these items is in this concern scale. So that little bit of future-proofing, thinking ahead of time about how you want to use this data set, ends up paying dividends when you actually handle this. So here's another similar example. This is a different section of the same data set. In this section, the reviewers in this study wrote actual critiques of the grant proposals that they were given. And I've stored those critiques as elements in the spreadsheet. So each of these chunks of text gets its own element in the spreadsheet. One of the things that we were interested in doing in this project is like looking for specific words that were used in the critiques and analyzing the uses of those words. So we wanted to do things with these chunks of text once they were stored in the spreadsheet. So let's say that I wanted, like, maybe I want a summary of the amount of text that was written about a grant's strengths. So I have these columns that say sig underscore text underscore str to indicate strength. Let's say that I wanted to pull all those together and do stuff with those variables, like count the number of words that go into each of those sections. I can follow a very similar process by using str detect. This time I'm looking for _str. And this $sign at the end, I'm not expecting you to know what it is, but I just want to make you aware that you can do stuff like this. The things that you search for are called regular expressions. And there are ways that you can indicate, like, I only want you to look at the very end of this chunk of text, or I only want you to look at the very beginning of this chunk of text. So I want to look for, any chunk of text that ends with _str. The $sign indicates the end of the chunk of text. So what this is doing is it's pulling out all the variables that end in _str. And these are those variables. Regular expressions, it's a very common way of dealing with text. This is another programming concept that if you took a dedicated programming course, you might get a unit on regular expressions. I just added a website link here if you want to read up more about this. They're really handy. They allow you to do some very powerful things if you're interested in working with text at all. It's a very useful thing. But I'm not expecting you to know it for the purposes of this class. So I'm just illustrating one thing you can do in a very fast way if you've thought about, indicating whether a variable is a strength. If I have all the variables that are the strengths of each of these grants, I can run this bit of code to get the number of times that the word cancer comes up in each of these sections in my data set. And I can do that in one line. The reason I can do that in one line is that I was sort of forward-looking the fact that I might want to work with the strength section of these data. That means I can do this very fast and efficient. Again, I'm not expecting you to know exactly how this chunk of code works. This is more meant to illustrate that this could be a substantively interesting question, like how many times do people mention the scientific content of the grades when they're talking about the grade strengths versus other stuff. Well, this is illustrating how you might approach that problem. Questions? Right, so just to be very clear about that, about what I expect you to know, you don't necessarily need to know how to use str count, but I do want you to know how to use str detect because it's just very, very useful if you're trying to do things on batches of things. So I'm not going to give an exhaustive list of all the different ways that this can benefit you because it really depends on what you want to do in your project. But I'll give you a couple extra tools that I find myself using a lot in with analyzing data. One is strc. That's just a way of smooshing together two chunks of text. And the other is str split. That's a way of splitting apart chunks of text. So one common thing that I find myself doing a lot is I often have scales. I work with closed-ended Likert type scales a lot. I often those scales just have item 1, item 2, item 3. There's nothing special about the items on that. They're different. So if I want to work with all the items in the BDI scale, and I happen to know that there are 5 of them, I can use strc to say, okay, take the chunk of text BDI, take the string of numbers from 1 to 5, smush those together. And that gets me BDI1, which might be item 1, BDI2, BDI3, BDI4, all the way up to 5. It's a very fast way of referencing a set of items that might go from 1 to 5 or 1 to 7 or 1 to 10, whatever. I find myself doing stuff like this a lot. I need to smush together 2 chunks of text, so it like generates some variable names. This is a fast way to do that. The reason that this works, of course, is that all the BDI items share that stem BDI. So this wouldn't work if you had chosen a different way of naming your variables. So let's say that you had a bunch of different columns called block 1 underscore response 1, block 1 underscore response 2, block 2 underscore response 1. So you had a structure, an untidy structure, where your variables were sort of composites of 2 different things, 2 different conditions, for example. If you separated those by an underscore, there's a function that can very quickly split up the variables or the chunks of text by that underscore. So if you use, say, the underscore as the delimiter, and you want to split up all of the variables by that delimiter, str split will do just that. And again, this only works if you've used a consistent delimiter. So know ahead of time that, hey, there are cases where I might want to split up the structural information about a variable from the content of the variable, or whatever it is that you use the underscore to separate. So that's another thing that comes up a lot for me. I have an example of doing something specific, so like figuring out which response each variable refers to. It's not super important that you understand how this code works. Basically, if you need to split up chunks of text by some delimiter, there's a quick way to do that. The big picture idea is that if you've built in some information about the structure of your data set into your variable names, that can be really powerful when it comes time to analyze your data. So instead of having to type out something like 10, 20, 30 times, well, if you've encoded some of that information in your variable names, that often leads to much more efficient ways of working with your data. This can save a ton of time. Not only because you have to type out or copy paste things fewer number of times, but because you make fewer errors. So if you're typing out something 10 times, or you're modifying, you're copy pasting, but modifying one thing, but sometimes 2 things, sometimes 3 things, whatever, that's an error-prone process. Efficiently naming your variables in a logical way can give you big efficiency gains. It also makes you less prone to error. So, there's lots of other stuff that you can do with variable names. I'm not going to go through an exhaustive list, but here's some tools, and there are other tools in this for your package. It can really save you a lot of time. I'd say this is one of the, as I've gotten more experience analyzing data, this is one of the places where I've made the biggest gains, is thinking ahead of time, like how do I want my data set structured? What kind of structure is going to help me do the things I want to do, and then being able to find efficient ways of doing these tasks. A few other thoughts about variable naming systems. So I've been talking about ontologies as a way of naming variables in data sets, but that big picture concept of an ontology applies to anything, including like how you name your files. So I'd shown this screenshot before of one way of storing multiple versions of the paper. I'm like going through the revision process. This right here, this file name is using an ontology. So there's first the name of the paper, the journal, and the date. That's information that I thought I might want to know when I go back to these files, so that I can, if I want to know, hey, where's the version of this paper that I submitted to Nature Community Behavior? Well, here are all the versions, and then here they are split up by date as well, if I wanted a version from the particular date. So this idea of like building in some structure to how you name stuff is a pretty big idea that applies to a lot of different places in your workflow, and it's also one that can be very powerful if you use it correctly. Another final thought is that the earlier you think about how you want your variables to be structured and named, the better. It's much easier to build in some of these ideas earlier on in the process of doing the project than it is to sort of put them on ad hoc later on. You don't always have control over how, say, your source data is structured, but sometimes you do. So, for example, if you're using Qualtrics, this is something that I use a lot, might be applicable to you all. If you go into that gear when you're creating a block of questions in Qualtrics and go into recode values, you can select this option, question export tabs, which gives you a way of naming the variables that you exactly as you want them named. That's something that I do a lot. I didn't used to do it. I found it extremely helpful. Another thing that you can do early on in the process is it's often good practice to do a small pilot of a project before you roll it out. Pilots in general are not useful for doing like power analysis, but they are really useful for making sure that the data set that you get is structured in exactly the way you want it structured, that there's no surprises. So that's one way that I use pilots quite a lot. Before I, test something out on hundreds of people, I might just test out, okay, is the data saving in the way that I want it saved? Is it structured in a way that's going to be convenient for analysis? Have I avoided any like unexpected surprises in the data set structure or form? So that's something that I recommend that you do as well. If you are trying to future-proof yourself against, unexpected errors or whatever, this is one way to do that. Check that your data sets are structured exactly the way you want them. So, big picture ideas. There are these things called ontologies, which are just ways of assigning words to concepts, words to variables. A good ontology will tell you which variables are which, so they won't have duplicate names. They're intuitive, descriptive, memorable. The good ontologies have names, variable names that are consistently formatted to avoid any sort of like typing errors. They're machine friendly. And ideally, they should tell you something about the structure of a project. And the ideal that you're going for is that if you double click on a data file and open it in, say, Excel, or just look at it using like the head command in R, that you're able to tell something about what's in this data set, the structure of the project that led to this data set. It would be really nice if we had standard ontologies in the behavioral sciences, but they're a little bit scattershot. So that gives you kind of a difficult task when you're thinking about how you want to structure your data. But one structure that's worked for me for variable names is you have like structural issues, blocks, whatever, early on, variable names in the middle, transformations at the end. Use a consistent separator when you're coming up with variable names. And the real benefit of ontologies is not only a way of like documenting what's in a data set for easy use, but it also makes you more efficient if you use some extra programming functions. And I recommend that you look into that if you want to be fast at this stuff. All right, thank you very much.